talk series. So CFP on fighters here. So today we have a guest speaker, Dr. Anthony Dosseto, Tony from the University of Wollongong. He's a senior lecturer at the School of Earth Science and Environmental Sciences down there. He received his PhD in 2003 from the Institut de Physique du Globe in Paris. I hope I pronounced
Very
that right.
good French accent.
Sorry for the French speakers in the room about that. He moved to Sydney in 2004, where he worked as a postdoctoral researcher at Macquarie University, and then in 2009 he moved to the University of Wollongong. He was awarded an ARC Future Fellowship down there, and he's the founder of the Wollongong Isotope Geochronology Laboratory, which is a research group interested in applying isotopic techniques to quaternary science, geomorphology, and archaeology. So yeah, I'll hand over to Tony, and then I hope you'll have some time for questions at the end, and then there will be lunch as well afterwards if anyone is interested. Thanks.
That's how you get people.
That's the selling point of these talks.
Thanks for that, Andrew, for organizing and Dietmar for suggesting this. First of all, a bit of advertising. We have a research group that's clearly not as big as EarthByte. Probably never will be, but we can only hope.
Gotta be optimistic. Huh?
Yeah, but we create these things so-called Wiggle. So if you Google Wiggle, not Wiggle, that probably gets sued for using that name. So just WIGL. That'll give you a little idea, although I should really update this website. A little idea of the different things we do. So like Andrew mentioned, quaternary science, archaeology, and geomorphology, things like that. Well, thinking about not using this pointer. Think about the Earth and what's really characteristic about this planet. Of course, there's many things, but one thing that's striking is how well regulated, so that's why I call that, IBM come up with that. But the Earth's thermostat, the temperature at the surface of the Earth, as you know, is quite well regulated, and this is the main reason why we're alive on this planet and not on others. Unfortunately, that sustains every type of life forms. Some could do without, but the bottom line is, thanks to that good regulation of the Earth's temperature, that allows life form to be sustained pretty much throughout. You know, you got the odd mass extinction, do we want one now? But we've sustained life throughout pretty much the entire Earth's history. So, and of course, the different processes that play together to control, to regulate this temperature at the Earth's surface. One of them is chemical weathering of silicates. So the mineral dissolution, the dissolution of silicate mineral consume carbon dioxide of the oxygen, and that's one way to control the atmosphere composition, and thus the temperature at the surface of the Earth. But we know how chemical weathering works. We know that consumes carbon dioxide. That's important to control the climate. But how does it work the other way around? Okay, how change in climate impact the way chemical weathering will operate at the Earth's surface? How does chemical weathering respond to change in climatic conditions? So how does it work? If you have a warming world, like right now, for instance, do you have more chemical weathering because it's a chemical reaction? So there is part, at least, of the reaction that's controlled by temperature. So you would have a negative feedback on warming. Okay, if it's warming, you have more chemical weathering, so you draw down carbon dioxide, you reduce the temperature. Or do you have more chemical weathering as a result of warmer condition because it's wetter, you have more humidity, you have more rainfall, causing more erosion, so supplying more fresh minerals to chemical weathering, and so then enhancing chemical weathering. So here again, acting as a negative feedback. Or do you have this kind of sequence where it's warmer weather, more erosion, but because you have more erosion, the minerals are moved, exported so fast through river basin that they don't have time to dissolve, they don't have time to weather, so you actually make less chemical weathering, in which case we would have a positive feedback. So when we look at Cenozoic in the early 90s, there was a really good paper that suggested that the cooling of the global climate that is recorded by oxygen isotope in foraminifera could be explained by the exhumation of the Himalaya. So uplift of the Himalaya, you create a mountain range, you have more physical erosion, which again would promote chemical weathering, increase drawdown of carbon dioxide, and decrease in temperature. That's one hypothesis. But then more recently, people have tested this hypothesis looking at the isotopic ratio of beryllium 10 to 9 in the ocean, so as recorded in iron manganese crust. And if you had, over the past 10 million years, if you had an increase in chemical weathering, you should see this isotopic ratio in the ocean decreasing, because that would mean more input from rivers, and rivers have a low 10 to 9 beryllium isotopic ratio. But you don't see, whether you look in the Pacific or the Atlantic, you don't see any significant statistical significant change in that isotopic ratio, and the authors concluded, well, we don't actually see any change in chemical weathering through the past 10 million years. So it's cooling really caused by more chemical weathering. This guy seems to think no. And then it gets really confusing because you have the same group of authors that can come up with very different interpretation to their own work. So in that first paper, they said, well, you don't really have change in weathering rates across glacial, interglacial cycles, because, well, when you have lower weathering rates during glacial periods, because it's cooler, it's drier, it's balanced by the exposure, so you have lower sea level, you expose continental shelf, you have a lot of carbonates, so they would weather quite rapidly. But then they came out with another paper where they actually suggest that, well, you could have rapid chemical weathering at the end of the last deglaciation. So it's a bit confusing, and mostly because, well, most of the proxy we use, they don't give us straightforward information on how chemical weathering is varying through time. So we try another proxy. So there's enough elements in the Verdi table to work with, to play with, and thankfully, thanks to ICP-MS, now we can analyze the isotopic composition about any element. So one of them, one with a lot of potential to look at chemical weathering, is lithium isotope. So you have lithium 6 and 7. For those who are not familiar with the delta notation, that's basically normalizing the isotopic ratio of the sample to the standoff. What's interesting with lithium is that these isotopes fractionate during water-mineral interaction. Not so much during mineral dissolution itself, but really most of the fractionation is occurring during interaction of water with secondary minerals, like clays, like iron oxide, and things like that. And what we find is that lithium is preferentially retained in the solid, in clays, so you have an enrichment in 7 compared to 6 in the waters. And experimental work, interestingly, showed that you don't have much differences in fractionation when you look at different types of clays, which is important because then when you go back in the sedimentary record, you could say, well, you see variation because you just have different types of clays. Well, hopefully from this work, that seems to be something we can discard. So initially people have been looking at waters, so river waters here in the Mackenzie Basin in Canada, and here some small rivers from Iceland. And what they found is some sort of relationship between the isotopic composition of the water and silicate weathering rates, so actual chemical weathering rates, where you have a high isotopic composition in the water at low weathering rates, and that isotopic composition decrease with increasing weathering rates. So then some people, Misra and Frolic recently have a very ambitious project was to reconstruct variation of the isotopic composition for lithium of the ocean. So they look at that, so they look at that isotopic composition, and they see an increase through the Cenozoic. Okay, here you have 60 million, 0. So they see an increase in delta 7 lithium throughout the Cenozoic, which they interpret as an increase in chemical weathering, responding to an increase in erosion rates, again, exhumation of the Himalaya. And of course, if you believe this interpretation, if I say that, then you hint that I don't, but I'll show you why. Then with that increase in weathering you would see from lithium, that would explain why you have this cooling, well, you don't see on this diagram, but it's cooling during the Cenozoic that is recorded by oxygen isotopes. The reason why I don't believe that is, I don't even know how that stuff got published, but because they got it completely the other way around. A colleague of mine actually tried to write a comment, and for some reason that didn't go through. It's interesting. But really, going back to these diagrams, you see that you have high delta 7 lithium at low weathering rates. So if ever what we should see from this increase is that these weathering rates throughout the Cenozoic are decreasing. Okay, so that's go down for increasing weathering rates. And I'm going to ask that a lot throughout this talk. Has weathering had any sort of effect on that global cooling? Because we observe a global cooling, but chemical weathering, if you get your lithium isotope right, are telling you something completely different. So that's, what they did is great, because you look at things globally that gives you, a picture of the evolution of the composition of the ocean. But what we try to do is to go back to basic and really trying to understand how these lithium isotopic variation are recorded in the sedimentary record. So we went in the upper Himalaya, in that region of so you have the Ganga River. So we went in the upper Ganges, upper Yamuna. So here we look at sedimentary deposit, and you have a record, and that's that picture you saw in the flyer. If you look, you have a record of sediment deposition in valleys and just outside the Himalayas that go back to 40,000, 50,000 years. So we can look at the last half of the glacial cycle, how those river and chemical weathering responded to climate change throughout the second half of the last glacial cycle. So we're looking at different areas. You got an alluvial fan here that we call the Donga fan. We also look at river terraces just when the Yamuna River exits the Himalayan range. And then in the lower Himalaya, we look at some terraces of the upper Ganges. So in the Donga fan, you have a record with these terraces and with this alluvial fan deposit that goes from about 9,000 to 30,000. The Yamuna River terraces, well, this is quite a small range, but that gives you, again, a point into the Holocene, so spreading between only 9,000 and 11,000. And the upper Ganges, so we have a series, that's these yellow pins, a series of river terraces, beautiful set here that you'll never see again because they're building a dam right there. So by now, that's soon to be completely flooded. The beautiful terraces that we have a chance to sample, and that goes from about, well, actually from the Holocene up to about 26,000 years. And going up, we got another deposit here between 35 and 40,000, and all the way up, something around 13,000. So we got different regions, but we cover basically the last 30, 40,000 years. Sampling, yeah, you have to be creative sometimes to do your sampling, especially when this guy decided that he wanted to sample up there. Not down here, quite hard. But also safety can be a bit of an issue, because when you look up and you sample some of this alluvial deposit that can be 50, 60 meter thick, you look up Of course, you're not wearing any helmet. And you see this, that would be the size of a small motorbike, but I probably would hurt a lot more than a small motorbike. So to actual results, so this is the sort of thing we see, so we're spanning the last 30,000 years. You got your delta 7 lithium here. The closed symbols are the bulk sediment, and the open symbols are the clay. So we separate the clay out of the bulk sediment and do an analysis on that. And what you see, this is the sort of range you get on the bulk, and this is the sort of range you get on the clay, simply because your information is in the clay. So when you just analyze the bulk, you're diluting your clays, you're diluting your signal with something that's just recording the composition of the bedrock, which is around here. But what both types of material are showing us is that you have an increase in delta 7 lithium where you're in the bulk or in the clays at about something between 15 and 20,000 years. So meaning, so higher delta 7 lithium being less weathering, lower being more weathering, so suggesting a decrease in chemical weathering at the end of the last glacial maximum, basically. So then when you compare that with what we think we know of the monsoon variability in this region, where you have an increase in monsoon intensity at about 15,000 years. So it looks like this increase in delta 7 lithium in those sedimentary deposits are synchronous with an increase in activity of the southwestern Indian monsoon. So a decrease in chemical weathering with an increase in monsoon intensity. So how do you explain that? That can be a little bit counterintuitive. Well, or not, because again, going back to one of the first slides, well, if you have more rainfall, as more intense monsoon would be, and that would also go deeper in the mountain range, you have more erosion, so your sediment can potentially spend less time in your river basin. So basically, the reactant, the sediment, spend less time in the reactor, the catchment, so you have less chemical weathering. You have less time for that chemical reaction to happen. So that's where only the younger in this room would probably get this slide, but that's where I like this video game. So that's where you feel the need for speed, and really you need some sort of constraint on how much time these sediments are actually spending in the reactor, actually spending in the catchment. And for that, I need to introduce the concept of comminution age. So I'm always amused to be teaching English to people being Frenchmen. But comminution, a lot of people are not aware that it's actually a real word. For those of you who are, I apologize, you need to be condescendent. But comminution simply means the process, the action of reducing to powder, pulverizing, and glacial geomorphologists are quite familiar with that term, because that's what glaciers do. Fluvial geomorphologists too, because that's what happened to sand grains where they're transported into the river. So by comminution age, we're gonna try, that comminution age we'll try to quantify is simply the time elapsed since the river sediment was produced from the rock at the bottom of the weathering profile, stored in the weathering profile, then exported and traveling throughout the catchment with possible storage in the alluvial plain. So that comminution age, once again, that we'll get from uraniumized stuff, encompass everything, the entire life of the sediment in the catchment until you go collect it. So again, storage in the weathering profile, transport in the river, and final deposition. So if you're able to constrain this age and the deposition age, and subtract the deposition from the comminution, you can reconstruct at the time of deposition, so go back in time, what was the sediment residence time in the catchment. And that residence time is the important parameter, because that tells you how much time the reactant minerals are spending in the catchment. So you can take sedimentary deposit, just for illustration, taking sediment core, and reconstruct your sediment, your paleo sediment residence time. So of course, if you're at the top, deposition age 0, imagine you can calculate the comminution age, you get 150, your sediment residence time is 150. And you can keep going like this. Let's say at the last glacial maximum, you get that sediment spent 60,000 years traveling around the catchment before being dumped 20,000 years ago. You get a sediment residence time of 40, okay, and so on. So then you can simply plot variation in sediment residence time as a function of time. And these variations tell you how efficiently the sediment can be weathered. Okay, if it's short, fast sediment transfer, less potential for chemical weathering. And how you do that? Well, you can try to quantify that looking at uranium isotope. Basically, the story is that if you look at mineral grain, and uranium-238 decays close enough to the surface of the grain, and by close enough, I'm talking about 30 nanometers, so really close. The daughter product, thorium-234, can be ejected. It can be recoiled, what we say, out of the mineral grain, and then lost in the surrounding medium, whether that's air or water. That thorium-234 decays into uranium-234, and that's how, at the surface of the grain, you will have depletion in uranium-234 compared to uranium-238. But if you look even this table at the surface within the first 30 nanometer, if that table was at least 40,000 years old, but I don't think this building is that old, you would see, you should be able to measure a depletion in 234 uranium. But of course, the surface to volume ratio of that table is way too small to be just grounding down the table and measuring that. You need to have small grains. So typically, we can observe this depletion when the grain is smaller than about a few tenths of micrometers, sorry. So basically what we date, your clock starts ticking when you grind the sediment, the rock, into something that's silt size. So to calculate your comminution age, well, you need two sort of parameters. You need what is the activity ratio in the sediment right now, and you need to know what is the fraction of daughter implied that you eject out of the minerals through recoil. And if you can quantify these two parameters, then you can calculate the age. That fraction, of course, is a function of the surface properties of the material. The higher the surface to volume ratio, like in the fine silt, the faster you will lose uranium-234, so the faster this ratio will decrease with time. And that's what we did in the same sedimentary deposit from the Himalaya, and this is the sort of results that we get. So here you have the deposition age, so we're going back again up to about 40,000, and the comminution age here. It's quite a new technique, so that was interesting to see that we can actually reproduce with different aliquots, reproduce these results by about 10 to 15%. That surprised me, really. I wasn't expecting that. But at least for me, it's quite satisfying. So then you can calculate your residence time, okay? Subtract the deposition from the comminution. This is the sort of thing that we get. So you see in the Yamuna terraces and in the Dong Fan, so between the Ganges and the Yamuna, so the square and triangles, you get residence time of up to 70, 80,000 years. So that means it can be quite surprising, right? That in these very narrow and deep valleys, you would have sediment stored for that much time. What we see on the other hand in the upper Ganges is that in the Alaknanda is that you see these diamonds, well, most of them are basically on the zero line. We can't, it's just going too fast. These sediments are moving too fast, so basically too fast means less than a few thousands of years for us to measure anything. So very different dynamic in sediment transport between the different regions. But what we do see, where we do observe some variation in the downward fan, is that you have a decrease in sediment residence time around ice peak stage 2, so what's cold, down by a factor of 2 to 3, down to about 20, 30,000 years at about 10, 12,000 years ago. And that's confirmed, at least for this part of the history of those catchments, by what we get from the Yamuna, where we do have about the same residence time. So what does it tell us? Well, it's interesting because, again, that fits with what we think we know of the paleoclimate in this region. Intensification of the monsoon, increase in erosion, faster sediment transport, which would explain why you reduce this sediment residence time at about, well, we don't have that much resolution, but let's say at around 20,000 years ago. So again, why is this parameter important? Why this sediment residence time is important? It's because that's going to be one of the key parameters when you want to calculate weathering rates. So don't worry too much about this equation, but what you need to worry about is that the time, like any chemical reaction, again, the time the reactants find in the reactor is important to be able to understand the extent of that chemical reaction. Well, first, from the upper Ganges, since we're not able to resolve this change in residence time, looks like this part of the world have very little chemical weathering, so a very small role on CO2 consumption. Again, basically because the minerals are just flushed out, so they don't actually weather. For the Yamuna and the Donga, well, it's a different story because we see that at about 20,000 years we have this sort of residence time, which if we use the previous equation with these parameters, will give you this sort of weathering intensity. Okay, so flux per area of weathering products. But if you decrease that by a factor of 3 as you go into the late Pleistocene and Holocene and this intensification of the monsoon, you decrease the weathering fluxes by about 50%. And then if you use that relationship we have for major rivers between weathering fluxes and CO2 consumption fluxes, then that means that, well, with this intensification of the monsoon, you would have decreased in CO2 consumption by about 50%. So let's look at what's happening at the climate at about that time. On the global scale, you have an increase in about 40% in atmospheric carbon dioxide in the deglaciation. What we see in the Himalaya is that we have a decrease in CO2 consumption by chemical weathering by about 50%. So that means, well, first, chemical weathering is not the driver of CO2 increase because it's decreasing its role on CO2. But certainly, it has a positive feedback where basically it's not stopping, it's not doing anything to buffer that increase in carbon dioxide content. So if we go back to this, you do have uplift and increased erosion and faster export of sediment. What we see in the upper Himalaya, is that you have less chemical weathering, and that would actually explain correctly the sort of observation they make for the lithium ice peak composition in the ocean, where you have less chemical weathering throughout the Cenozoic. So again, if we do have less chemical weathering throughout the Cenozoic, what is causing climate cooling? And like I was telling Dietmar earlier, chemical weathering is supposed to be the backbone of my business, but the more I look into it, the less I believe that it's actually playing such a significant role on the global climate. But that's just one aspect of the picture. Now I just show you what's happening in mountain ranges, and that's only one side of the story. Okay, you don't only have mountain ranges at the Earth's surface; you also have alluvial plain, And what is happening in terms of chemical weathering in these alluvial plains? What is the response of climate change? What is the response of chemical weathering when you have climate variability in alluvial plain? So what is the role of alluvial plain on chemical weathering? Well, some recently said it's really important, and it's actually so important that mountain ranges don't play so much of a role. Generally, we think, the common paradigm is to say, well, you have a lot of erosion in mountain ranges, so you supply a lot of fresh minerals to chemical weathering, to fluids, so you do a lot of chemical weathering in mountain ranges. What this paper says is that basically you have most of the erosion fluxes are coming from lowland areas because they're greater surface than mountain ranges. So even if the plains, lowlands erode slower than mountains, of course, but because they cover such a large area of the continent, they're actually the main contributor of sediment fluxes. Then more recently, these guys at AGU last year will actually show that, well, depending on the digital elevation model that you use, if you use something with a low resolution, yeah, you can come to this sort of conclusion because of the low resolution of your DEM, you think that, well, you don't have much of a surface of mountain ranges. But if you use a higher resolution DEM, you see that, well, the actual surface of mountain ranges is greater, then they supply, of course, a lot more sediment fluxes. So what is the role? So that's for sediment fluxes, that's for erosion. But what is the role of alluvial plains on chemical weathering? Well, you can look at different places. You can look at the Amazon, so that's the upper Madeira. The Madeira is one of the main supplier of sediments to the Amazon. And what we found a few years ago is that if you use a chemical weathering index, so that alpha sodium basically means that the greater the value, the more chemical weathering is occurring. The continental crust will be down here, and what you find is that, well, when the sediment exits the Andes, it already has been weathered, well, half of the weathering flux is happening in the mountain range, and the other half, that's the final composition of the sediment when you reach the Amazon, the other half of that chemical weathering is occurring in the plain as the sediment is traveling through the floodplain. So that's what you see with this increase in residence time. So from this region, it's half-half between mountains and alluvial plain. More recently, some others look at the main stem of the Amazon River, and what they found, so comparing the chemical composition of the sediment before, so when it enters the floodplain and when it exits the floodplain, they don't see much differences. So basically, if you're in this band, that means that the chemical composition of the sediment that comes out is the same as the chemical composition that came in the floodplain. And except calcium, they see that floodplain in the Amazon seems to be, at least in this region, seems to be playing not too much of a role. Then in the Ganges, they get another story, and again, it's the same group of authors, more or less. It's quite interesting. But they get a completely different result, where they see that as the sediment is traveling throughout the Gangetic floodplain, you have decreased, you have a loss, continuous loss in sodium, so your sediment is continuously weathered. So we tried recently, and we're still working on that, to use New Zealand to try to get the Amazon and the Ganges to agree. Of course, much smaller rivers, much less intense climatic conditions in terms of rainfall and temperature, but quite interesting because you have this mountain range, very short rivers on one side, very longer rivers crossing an alluvial plain on the other side, and similar geology and a range in climatic conditions. And what we find is this. So this line up here with the dashed line is the average composition of the parent material of the bedrock with the error. And this is what we measure in sediment, so along the channel, so throughout the floodplain. So what we see is that as soon as your sediment left the hill slope, it's already weathered. So you have a loss of things like sodium, like strontium, compared to immobile elements like zirconium. But once it's traveling in the river and crossing the alluvial plain, you see relatively little change in these geochemical parameters. So New Zealand seems to say that, well, most of the chemical weathering is occurring on the hill slope, and very little during transflow. So if I try to summarize that simplistically in the table, you see in the Madeira it's 50-50. The Amazon, well, the plain is not really. The Ganja, well, the plain would be actually the major place where chemical weathering is occurring, and you would have the opposite for New Zealand. So we really need to know what's happening in this alluvial plain, because they seem, at least in some cases, they seem to play a role on chemical weathering. The trivia bonus, if you want to win a shirt, I love geomorphology. Seriously, they actually sell a shirt like this on the internet. It's quite appalling. But the bonus question would be to try to understand why some fluvial systems give a lot of importance to chemical weathering in floodplains like the Ganges, while others, like the Amazon or rivers in New Zealand, seems to have floodplains where chemical weathering has much less effect. So to conclude, at least to me, hopefully I made the seminar confusing enough, it's not clear that you have an increase in chemical weathering when you have an increase in erosion, at least from the lithium isotopic data we get from the Himalaya. So again, it's only one part of the picture, because we're in the mountains. We don't see an increase in chemical weathering and an increase in erosion. This second point is actually wrong. I'm oversimplifying, because I'm talking about Tibet Plateau exhumation. Okay? I'm talking about tens of millions of years, which would cause an increase in erosion, but maybe the chemical weathering response is different than what I actually get from my little study, because my little study was looking at the effect of climate variability, of change in monsoon intensity. We keep relatively tectonic constant over the 40,000 years. So this is different time scale. So we could have different responses. But really, the conclusion, at least to me, to try to think about these questions is that, well, a strong role of chemical weathering on global climate, really, that's not obvious. And of course, other processes control the composition of the atmosphere, control global climate, one being carbon burial. And if you look at carbon burial throughout the Cenozoic, and that's what these guys did back in 2007, well, you could explain why you have cooling during the Cenozoic, because if you have emergence of the Himalaya, increase in erosion, which can boost carbon burial, because you have entrainment of a lot of vegetation, including throughout sediment transport throughout the floodplain. So you boost your carbon burial, you trap carbon, you reduce carbon dioxide from the atmosphere through the organic pathway, and you can then account for your global cooling throughout the Cenozoic. But what about if we go further back in history, and that's one reason why I'm here, is to talk about tectonic plate configuration and how at the scale of the Phanerozoic that could play, I believe, but I might be wrong once again, back with chemical weathering, could play a major role on the global climate. I mean, there's the obvious effect on atmospheric and oceanic circulation, on volcanic gas emission fluxes, but they are also things about plate configuration that will be important for chemical weathering and for carbon burial. Things like the ratio of mountain to plains. Okay, if you if you are in a scenario, and again, what I showed here doesn't really prove that, but if you do have a supercontinent, so one thing, I suppose, is that you would have low ratio of mountain to plains. Okay? You would have mountain ranges at the plate boundaries, but in the middle, you will eventually reach peneplain. So in this case, and in the scenario where chemical weathering is more important in mountains than in plains, you could have little chemical weathering during episode of supercontinents. There's also the climatic effect of continentality. Okay, if you have a huge continent, you have a huge continentality effect with all the rain, all the moisture dropping at the margin, but right in the middle, of course, there's nothing. And that could be also a factor for reducing chemical weathering. And there's the effect on vegetation. If you have supercontinents with, again, these large continentality effect, well, if you have very arid interiors with scarce vegetation and with little potential to produce this organic carbon that you can then bury in the sedimentary record and use to reduce your carbon dioxide content. That's it. I'll be very happy to take any questions. So everybody's convinced about the amount of confusion I try to generate.
So what's your take-home message?
That I'm increasingly skeptical that chemical weathering is as much as a major driver as we think it is, as a lot of people think it is. So, yeah, and I would favor, at least for the Cenozoic, and again, you have to look at sort of time scale, because when I talk about lithium in the Himalaya, I'm talking about a time scale where that's going to be more about glacial cycles. But if you look at the Cenozoic, you're looking at a time scale where the plate tectonic configuration is going to be important, where tectonic, where uplift is going to be important. So it's also a matter of time scale.
I have a comment on the question, but I tend to talk a lot, so I wait because somebody else wants to ask a question before me, but that doesn't seem to be the case. Right, so what about chemical weathering of the oceans, or in the oceans, of the ocean floor? Right? So that's something you didn't talk about, but that's perhaps something that one should also consider. Right? So seeing that a much larger portion of the world's surface is covered by ocean floor, and so chemical weathering of the ocean floor happens by means of hydrothermal circulation. And again, most people are so there's a bit of an enigma there that's akin to looking at chemical weathering in mountain beds versus the alluvial plains. Right? When it comes to chemical weathering in the oceans, many people are quite preoccupied just looking at the vigorous hydrothermal circulation that happens right at the mid-ocean ridges. Right? But in fact, hydrothermal alteration continues on the ridge flanks for many tens of millions of years. Right? And so we had a paper in geology last year where we looked at the effect of mid-ocean ridge flank weathering on calcite versus aragonite oceans through time. And so how that affects the abundance of calcium versus magnesium in the oceans. But there was also there was something that we had originally in the paper that we took out, which had to do with CO2. So there was a paper by Richard Gerard a long time ago who compiled ODP data from DSTP data from ocean crust. And he noticed that there's also a large increase in the CO2 content in the upper weathered ocean crust as time goes by, and it increases even for many tens of millions of years, right? And he came up with the interesting hypothesis at the time that in the Cretaceous period, when we had a hothouse climate for a long time, right? There were lots of mid-ocean ridges that formed as the Pangea broke up, right? And the total area of old ocean floor that has the capacity to absorb more and more and more CO2, mainly through precipitation of carbonates and veins and pore space. So there was much less old ocean floor around, right? And so the total capacity of the ocean floor to store CO2 was in fact much diminished compared to the Cenozoic when we observed cooling. So the cooling trend in the Cenozoic is in fact coincident with a vast increase in older ocean floor that has a larger capacity to bind CO2. There's a reservoir, there was a growing reservoir of CO2 in the upper ocean crust. And but I don't think this is something that anybody has ever considered in carbon budgets. It's just an interesting idea, perhaps.
Yeah, that's a good point. I mean, you know, like most scientists, I'm only looking at one aspect of the problem, and I kept my head above the water. At least I tried, literally. But yeah, certainly what's happening. I mean, like you say, you know, it's a large surface, obviously, so that can play a great role.
Might be interesting to try to quantify that effect, and and start looking at weathering of the ocean floor as well, not just the continents. How that changes through time.
Well, and I guess from the ocean, we actually, with the IODP program, we get better record. Better sedimentary record than we have on the continents.
Yes, that's also true. Yeah, unfortunately, the ocean drilling sites on old ocean floor that drill all the way to basement are very rare, you know, because most people are more interested. It's easier to cast an ODP proposal around recent climate change, so that you only have to drill, you know, the upper portion of the sediments to capture, say, the late Cenozoic history, and oftentimes there's no need to drill through the entire sequence, you know, then you never get a sample of the ocean process, you know. That introduces a bias there.
Yeah, but drilling, you know, across, then you use, you know, your distance for time. So you can use the age of the oceanic crust as, you know, going back in time. And yeah, it's going to be maximum age.
Yeah. No, but you're right. So there's a much better sedimentary archive in the oceans, and there are plenty of holes by now.
Oceans aren't very different to the land, though. Like the ocean reservoir absorbs more CO2 than the atmosphere, so it's completely different to what you're saying. Because it's known that the acidification of the ocean and the carbon compensation depth is actually rising. So I think it's just completely different studying the ocean to studying what you're studying.
Yeah, that's why people. That explains why people tend to stay either on the continents, just study the continents, or just study the oceans, because they're so different.
Yeah. But no, that's a very fair point. I mean, you know, if you want to tackle that properly, you need to look at all aspects, and yeah, you can't just look at the ocean or the continent.
And also the sea level and in the high altitude, also the differences in hemisphere. Yeah, because the Tibet plateau is very high and cold, it's not easy for the chemical variant. But for the sea level, which the weather is high, it may be easier. So maybe this cannot compare.
Yeah, well, that's why some people suggest this as one of the papers that was showing clearly, that if you have lower chemical ordering during glacial period, that could be counterbalanced by the exposure of continental shelves, where you have rock, like you said, that can be quite easily weathered.
So
question correctly, that a lot of people are kind of obsessed with the Himalayas as being like altitude. So I just want, I mean, there must be other factors in a really general sense that affect weathering. Like, for example, does latitude affect weathering?
Well, that's a good point. I mean, that's what I'm also interested in, the plate configuration, because depending where your mountain range will be, if the Himalaya was, you know, at the same latitude as Scotland, you'd probably have,
I guess, like, forgetting about mountain ranges for a second, if you take Australia, then Australia's drifted a long way northward in the last few million years, right? So does that mean that forgetting about all the rest of the world, then the weathering contribution of Australia would have changed a lot because it's drifted northward? Is that not maybe?
well, I guess, I can't, of course, give a definite answer. I would suspect that Australia is a bad candidate for that, because it's already so weathered that whether you put it in a wetter area, I'm not sure that would make much of a difference, because if you squeezed out of the rocks, you know, everything you could, and that's the case in many parts of Australia, where everything, all the minerals that could easily dissolve, they're gone. Then if you take that continent and put it in a wetter area, it's not much more you can do, basically. So, but that would be, with the continent that would be a bit more fertile, if you like, where you still have a lot of minerals that you can dissolve. You would suspect that would have, mountains or not, that would have an effect. If you put your continent in an environment that's wetter and warmer.
So you'd want to look for an area where the kind of age of the crust was relatively, I think that was an ecology.
Yeah, or simply looking from the plate configuration perspective, looking where are your continents. If you put all your continents, around the equator, then you're going to be more likely, well, you're going to be doing different sort of things, but I was going to say more likely to have chemical weathering than if you have them all at the poles. All the poles, then you have more glacial processes which produce very fine material, which is then more prone, if you do have some temperatures that allow chemical weathering, but you have material that's potentially very fertile for chemical weathering. So I did not answer your question.
No, that's okay. But no, well, actually, so for example, with Antarctica, like how, having an ice sheet or not, is it still like a bit of an open question as to whether that will produce an effect in one direction or another?
Which direction?
So, well, I don't know. If you have a whole continent where at one period in time it has an ice sheet on top of it and then it disappears, or the other way around, then is it clear whether that would increase weathering or decrease weathering?
Well, I mean, commonly what we think we know is that, well, when you have an ice sheet, you reset. So any soil that were there, they're eroded by glacier, by the ice sheet. So you reset your landscape. And then when the ice sheet retreats, well, if you have bare rock, that's not going to promote chemical weathering much, because a bare surface, a bare rock is difficult to weather. You need surface to do chemical weathering. But if you have retreat of an ice sheet, and you have glacial flour, you have moraines, you have material that can be weathered, that can potentially really promote, that can really kickstart chemical weathering. And that's the sort of thing we think we see in Canada, in the Mackenzie Basin, where we see that all the sediment have the residence time of about 20,000 years or less, and we think, well, basically that's where they're produced. When you have retreat of the ice sheet and then you expose the sediment and they really start to chemically weather.
Yes, I have one more comment or question. So the type of rock that you are exposing for weathering must clearly make a difference, right? Yeah. And so there was an interesting recent paper by Dennis Kent from Vermont and somebody else whom I can't remember, in which they tracked the history of large English provinces through at least the Cenozoic, if not into the Cretaceous, I can't remember. And so they made the case that when you have a large igneous province that crosses tropical latitudes, that the intense weathering of those solid rocks that are very easy to weather, maybe easier than more silicious rocks, that leaves a signal in global climate.
Yeah, it's really interesting.
Yeah, and so that's very different from the argument of mountains versus plains. That's actually the type that you create a large body of rock that's quite easy to weather. It might not be very elevated, but it's at the surface.
Yeah. Well, one of the other things I'm looking at is how fast you produce weathering profiles, how fast you produce soil, and how fast that weathering from migrate into rocks, which is where most of the chemical weathering is occurring. And what we find from a few studies on different rock types, different climate, is that really, as expected, is the rock type that matters most. Where you have granite in different, in Puerto Rico or down in the Big Valley, we get about the same rates. In which then, I'm not going to get started on that, which then is very interesting because you have total decoupling between the bottom topography of your weathering profile and the actual surface topography. What's happening between these two interfaces, these two boundaries, is controlled by completely different things. But yeah, lithology, big thumbs up to control weathering. Yeah.
I think there's scope for developing a sort of a weathering plugin for G-plates, where you can imagine you have the digital geology. Yeah, you have the digital geology, that you track around, and then you can parameterize the capacity of different rocks, how they weather, say in a latitude-dependent way. And it surely makes a difference whether they're in a monsoon-prone hot region or not, something like that.
But some people, Musdorf and another guy, I don't know his name, they did that where they looked, so they like global maps of everything, so they took global lithology, and they look what we think we know of weathering rates of different rocks, so they look, make a map of chemical weathering rates. But as far as I know, they don't look back in time.
Yeah, so I think
start moving these rocks around.
But I think that could be very interesting.
Hey, cool. Troops are hungry.
Yeah, I think so.